Figures 14.2 and 14.3, building a stack class template. In this example, we're going to, for the first time, use the concepts of templates to create our own templatized class that can then be specialized to work with different types. Now, we've already introduced to you back in the arrays lesson the vector class, which is part of the C++ standard template library. And in the last lesson of this Live Lessons product, we'll be taking a look in more detail at a bunch of predefined templates that are provided by the C++ standard library. In this example, we're going to implement our own stack class to demonstrate some of the concepts of building your own template. Now, when you're defining a class template, you typically define the entire class template either directly in the curly braces of the class or in a header file that consists of the class definition followed by the member function definitions. And the reason for that is the vast majority of compilers require the complete template definition to be available to them in each of the compilation units where you wish to use the class template. So same thing with function templates as well, by the way. When you define those, you typically place them in header files for reuse in other compilation units. Now, when you introduce a class template, you do so with the template keyword, just like you do with a function template. And so here we see the template keyword followed by type name T, introducing T as some generic type name that will be used throughout the class definition. Now, by the way, you can have as many templatized type names as you need for a given class. In our case, we're taking the simple approach and just having a stack of some type, but if you needed to create a template that required multiple different type parameters, you can have a comma separated list in here, just like you can for a function definition, for example. So here we have our class called stack, and we have a public interface to the class as well as some private data. Now let's take a look at the private data first, where we have an integer called size that represents the total number of elements in our stack object. We have an integer called top, which represents the index number of the current top location in our stack. And then we have a pointer of type T called stackptr, which is going to point to the dynamically allocated array that represents the stack's internal data. And basically, let's say we create a stack of integers, we will then allocate dynamically an integer array under the hood of this class to store all of the integers that are placed into the stack, and the top integer is going to represent where the current top of the stack is at any given time. And for those of you who may not be familiar with the stack data structure, basically it's like a stack of dishes. You always put something in at the top of the stack, and then you always take something out from the top of the stack as well. Now let's go back to our public interface, where we have a constructor that says that it receives a single integer with the value 10. And by the way, we really should be declaring this as an explicit constructor because of the fact that we don't want this to be potentially used as a conversion constructor. You may recall from the operator overloading chapter that any constructor that takes one argument of a type that's different from the class type is considered to be a conversion constructor by default and could potentially get used accidentally to do an implicit conversion at compile time. So we have our constructor that takes an integer as an argument, and that represents the default stack size for that particular stack object you're creating. If you don't specify a value, you'll get a stack of 10 elements. We also have a destructor, and the reason for that is we will be dynamically allocating the memory in which we store our data, so we need to provide a destructor to dynamically deallocate that memory when a stack object goes out of scope or is removed some other way. We have a push and a pop member function. The push member function receives a constant reference of type T to represent the element that's being placed onto the stack, and pushing an item onto the stack doesn't modify that element. That's why we declared it const. We also have a pop function that receives a reference of type T, and basically we're going to pass a variable into the pop function, and the pop function will store the value being removed from the stack into that variable. both of these functions return bool, in our case, to indicate whether or not they were successful. We also have an isEmpty function, which is simply going to return top double equals 1. We're going to use minus 1. We're going to use minus 1 to indicate when the stack is empty. Minus 1 would be, if you will, the index number right before the first position in the array, which has index number 0. So if the top is currently minus 1, that would indicate nothing is in the stack. As soon as we put something into the stack, we'll increment the top to make it 0, and then we'll increment it again to make it 1, 2, 3, etc. And every time we remove an item from the stack, we'll subtract 1 from that value. And we also have an isFull function to test whether or not we've filled up all of the elements of the array. Now, for the destructor, the isEmpty function, and the isFull function, because they're fully defined within the class definition curly braces, they are also implicitly inlined. And as you can see here, each of these functions is actually very straightforward in terms of its body. Typically, the compiler would inline such simple member functions for performance reasons. Now, separately, right below the class, we have a couple of additional member function definitions. And if you are going to define a member function outside of the class, you must specify that the function is within the scope of the class. Now, any member function of a class which is a class template is going to be a function template. So we start with the same template line that we have at the beginning of our class definition. Then we specify the scope of which class this particular member function belongs to. And the thing you have to keep in mind is that there's a separate version of this constructor for every different specialization of the class stack that gets produced. So we can't just say stack : on the left side here. We have to say stack angle bracket T angle bracket to indicate that for whatever customized type we are generating, this particular version of the constructor goes with that particular version of the class. So if I say I want a stack of integers, there will be a constructor that is customized for the stack of integers class. If I say I want a stack of employees, I will get a custom constructor for a stack of employees, and it will be associated only with that version of the stack specialization. So our constructor, as you can see here, receives an integer representing the size. In our member initializer list, we're initializing the size, and notice that we've put the conditional expression to validate the size right there in the parentheses within the member initializer list. So if the size is greater than 0, we'll use it. Otherwise, we'll implicitly set it to 10 in our example. The top is being set to -1. The stack pointer is actually being initialized here as well with a dynamically allocated array of type T with size number of elements. So again, if I'm creating a stack of integers, in this stack constructor, T would be replaced with int, and I would allocate an array of integers. If I'm creating a stack of strings, then T would be replaced with string, and I would allocate an array of strings. The body of the constructor is empty because we did all of the initialization in the member initializer list, and in general you should do that with all of your classes if you can. Anything that's too complicated to do in the member initializer list can be done in the body of the constructor. And down below here we also have our push and pop member functions, which complete the class definition. Again, they are templates as well because they belong to a class template. And here we're saying that the push member function belongs to the stack of T class, where T is going to represent the type that's stored in the stack. When we're storing a value into a stack of type T, we need a value of that type to be passed into this function so that it can be placed into the stack. So if it's a stack of integers, we need an integer to be passed to this function. If it's a stack of strings, we need a string to be passed to this function, and T represents that generic type. So here we're going to receive what we call the push value as a reference of type T constant, meaning that we're not going to modify whatever that thing is when we push it onto the stack. As long as the stack's not full, we will take the current element of the stack PTR array that's been dynamically allocated, assign push value to that element, and increment the top integer, which represents the top of the stack, at the same time. So in terms of the order in which things happen here, first we'll increment the top counter. That moves us from whatever the previous location was to the next position within the stack. If the stack was empty, that moves us to element 0. Then we assign a value to the stack pointer dynamically allocated array. Now, notice we're using an assignment operator here. So whatever we're going to be assigning into the stack has to have an appropriate assignment operator. And remember, every single class gets an assignment operator by default. If you have a class that has dynamic memory associated with it, you would typically have an overloaded assignment operator for such a class. And back up here, we didn't have any operator requirements for the purpose of the constructor. We do, however, have to have a default constructor associated with whatever type we're allocating, because when you create an array of a given type, it's creating objects of that type, and those objects need to be initialized. So if your class does not have a default constructor, you won't be able to use it with our stack class. Let's go back to the push function here. If we're able to successfully push a value, we'll return true, and otherwise we'll return false, which would indicate that the stack was full and therefore we could not push a value. And we'll use that in our test program. We also have our pop function, which is going to place the popped value into its parameter. If the stack is not empty, we will assign to pop value stack pointer subtop minus minus, which uses the current value of top to access the dynamically allocated array. After doing so, it decrements the top integer to indicate that now the top of the stack is one position prior to where it was before. And again, we're using the assignment operator here, so we have to make sure that for our class, assignment is going to work correctly for objects of our class. At line 71, we have a return true to indicate that we successfully popped a value. Otherwise, we will return false to indicate that the pop was unsuccessful. Now, we've created this template and we want to use it in a program. So here in main, we include the stack template definition by including its header file, and then we start using our stack. Now, you may recall when we introduced the vector class that part of defining an object of a template class, or a class template, excuse me, is to specify what type you want to use within the template. So in this case, we're creating a stack that is going to be capable of storing type double. And we can refer to this as stack of doubles in terms of how we read the data type. So we're going to call our stack of doubles double stack, and we're going to give it an initial size of 5 elements. And then at line 12, we're going to create a double value of type double with the initial value 1.1, and we're going to demonstrate pushing some elements onto the double stack. So here you can see that we're going to keep pushing until this while loop condition fails. Double stack.push is going to return a Boolean indicating whether or not it was successful. We're going to push the double value, then we're going to display what we pushed, then we're going to increment the double value by 1.1. And if we stop here, actually we'll go to line 23 first and show you that once the loop terminates, we'll print out stack is full, cannot push, and we'll show you the last value that couldn't be pushed. So if we stop there, you can see pushing elements onto double stack. We were able to push a total of 5 elements, then the stack was full, and we could not push 6.6, and that makes sense because we only have 5 elements in this stack. The next thing we want to demonstrate is popping elements from the double stack, and we use a while loop to do that as well, and it will keep popping as long as pop returns true. Each time it pops, it will place the popped value into the double value variable, and then we will output that value followed by a space. Then we'll print out when the stack is empty and we cannot pop anymore. So if we stop there, you can see popping elements off, and in the case of a stack, elements always are popped off in the reverse order from which they were pushed, because a stack is a last in, first out data structure. So you can see the elements in reverse order. The stack is then empty and we cannot pop anymore. Now, when we initially declared this stack of type double, what the compiler did is it took the type double and then it replaced every occurrence of t within this class definition with double generating a complete customized version of class stack, a specialization, if you will, that is geared towards working only with data type double. In main, when we go to the next part and we say now we want a stack of integers, first it's going to check to see if it's already generated code for a stack of integers, which it has not. Then if it hasn't, it will take the type int and it will go replace every occurrence of t within this template with the type int, producing a specialization that is geared towards manipulating only type int. And once we've done that, we can then go back to main and test out that stack. Here we're going to declare the integer int value and initialize it with 1. Then we're going to do the same basic operations we did up above. We're going to print or push a bunch of values onto the stack as long as it is still has remaining spaces. In this case, we created an int stack with the default size of 10, so this loop should iterate 10 times and push the values from 1 through 10 onto the stack. And as you can see here, each time the while loop condition executes, we push the current int value. We then output that value, increment it after we output it, and follow the output value with a space. And then when we come back around to the condition again, we push the next value. And if we stop there, you can see that we're pushing elements onto int stack. The values from 1 through 10 get pushed, then the stack was full and we could not push the 11th value. And then finally, we pop the values back out using the same techniques we did up above, and you can see that indeed the elements come out in the reverse order. So clearly, our stack was able to be used with two different specializations, one for type double and one for type int, and it can be used technically with any class that properly supports the assignment operator and has a default constructor as well. So for example, we could easily create a stack of the C++ standard library class string, whereas for some of our other classes that don't have default constructors, for example, the employee classes in the polymorphism chapter, we would not be able to use those classes in this example because of the fact that they don't provide a default constructor. And that's going to be a consideration that you have to think about when you are using your own data types with the standard template library classes. There are going to be restrictions such as which operators you need to use or need to have available for your types to be able to use a given template. Also, whether or not you need a default constructor is going to be important, so you're going to want to look at the requirements of a given template before you use it so that you fully understand how your data type needs to be defined in order to work properly with a class template.